Okay. Hello. After a long break, we continue our optimization course. This is lecture number 11, Conjugate Gradient Method. And so the previous lecture was about was the beginning of the development of this method, which was called Conjugate Directions method. And we showed that in order to minimize a quadratic function, we can do it in simple way if we have a set of so-called Q conjugate or Q orthogonal directions. Conjugate gradient method is a simple consequence of what we already know if we build our set of conjugate directions on the base of gradients of the function in the points which we pass. So let's start. So we have a quadratic function. We will denote its gradient gk. It's its gradient f at the point, some point xk. And we can even write it directly. So it will be q xk plus b. And let's rewrite the conjugate directions method as we already know it in terms of directions linked to the gradients. So we start d0 is just minus gradient at the beginning, at the starting point x0, and we can even open it's minus q x0 plus b. Okay, step k. Xk plus 1 is equal to xk plus some step size gamma k multiplied by our direction which we already have, dk, and here we have to use so-called exact line search. So do exact minimization in gamma of our function. And then we compute a new direction, as we already used to do in conjugate direction method. So we have our new vector which we orthogonalize is minus gk plus 1, and plus this term which we already saw in Gram-Schmidt formula, j me 0 from 0 to k, jk plus 1 transpose q dj divided by dj transpose q dj multiplied by dj. So this is Gram-Schmidt for Q orthogonality. orthogonality of set of vectors dj. You can write even j from 0 to k. Okay. Okay, so we got this formula for computing conjugate directions. I write it once more. And why conjugate gradient method has advantage over a general conjugate direction method? It's mainly because this, not mainly, but one of reasons, because this formula is greatly simplified when conjugate directions are built on the base of gradients. So we have two simplifications. The first of them simplification 1. Let's look what is the direction dj? Because of line search, dj, if you remember, xj plus 1 is xj plus gamma dj. So I can write that dj is 1 over gamma j, xj plus 1 minus xj. And therefore, the term q dj, which we use in numerator and in denominator, q dj, I rewrite this as 1 over gamma j. Q xj plus 1 minus xj. And if you remember formula for the gradient of our objective function, it was qx plus b. So here is just difference of two gradients. 1 over gamma j, j plus 1 minus gg. Okay. The second observation, still in first simplification, I should remind you expanding manifold property, which we learned in previous lecture. It says that at every step of conjugate direction, we get minimization of our objective function over a subspace, affine subspace spanned by all previous directions. And because we build every direction as a combination of previous gradients, so we minimize also over subspace spanned by all previous gradients. And as we told in previous lecture, this means that new gradient must be orthogonal to this subspace. And I write it explicitly by expanding manifold property. G k plus 1 is orthogonal to gk, gk minus 1, g0. Okay. So, and we have this scalar products of gk plus 1 with differences of gradients. So we can see that all terms in this sum vanish except of the last one. So we are left with only the last term. Oops. In the sum. Namely, dk plus 1 is equal minus gk plus 1. And I substitute what we already know. Gk plus 1 transpose gk plus 1 is gk divided by dk transpose gk plus 1 is gk multiplied by dk. Okay. Okay, so we got this a bit more simple formula, and we continue simplifying even more. Simplification 2. Sorry, it was dk here. Let's denote in this formula for new direction, it's like gradient plus some scalar multiplied by previous direction. So let's denote this scalar as beta k. So we have this generic form. We have d k plus 1 minus gk plus 1 plus beta k dk. Okay. What we have in denominator? Let's try to see. So actually gk plus 1 is orthogonal also to dk, because dk is the last element in the subspace which we did optimizations. So let's denote this formula x star and write the denominator of star we have dk orthogonal to gk plus 1. It's a and b, which we have in b. Let's open the expression for dk. It's like minus gk. It one step back in our sequence, minus gk plus beta k minus 1. Dk minus 1 multiplied by minus gk what is written here? Okay, sorry, I forgot this transpose. So what for is B? So we told that this vanished because of orthogonality, and now we consider this product. And what we say that this is orthogonal to GK. It's like previous iterations, so we can remove also this, and therefore we remain in dominators just in GK with GK transpose GK. And so what we get finally, let's summarize. Finally, we get beta k is equal to gk plus 1 transpose gk plus 1 gk divided by, I even can write shortly, gk 2 norm squared scalable of vector by itself. And this formula has name Pollack-Rieber method. Pollack-Rieber. Actually, we could simplify nominator even more and get even simpler formula. I will write it separately. Beta k is gk plus 1 transpose gk plus 1. Actually, I can write here on 2 norm, it's correct, yeah? gk plus 1 norm squared. Yeah, it's really nice simple formula. gk squared. And this formula also has name Fletcher-Reeves. So we have two formulas which in our case are equivalent. Why do they exist separately? The reason, if we just in a moment will generalize the method for general non-quadratic function, these two will behave differently. And interestingly, this formula, which seems somehow a bit irrational, numerically behaves better, and people prefer for non-quadratic optimization this kind of foundation. Okay, so we finished derivation of the method, so let's just summarize. Here is a summary of the algorithm. So we start at some point, and I write it in general form for general nonlinear function, despite the development was for quadratic function. So this is our first starting direction, d0. Then we update our axis, it's called new iterate, just by line search in corresponding direction. And compute new gradient and compute future direction. And for general nonlinear optimization, as I already told, the Pollack-Rieber update is recommended. Some theoretical consideration, which I will not get into, and numerical practice also shows that it's better to use it. I just want to say that if we have quadratic function f, so we can do our computation in a rational way, and one should be a bit careful about this. So let's do in parallel what will happen for quadratic function f 1/2 x transpose qx plus b transpose x. Okay, so what will be our G0? It's minus q, minus, we have minus G0. Minus q x0 plus b. Okay. Now, line search. For general function, we really need to work hard to do polynomial approximation or whatever to do accurate line search. And by the way, I should stress that for nonlinear optimization, it's critical for conjugate gradient method to use exact line search. In contrast to other, if one use gradient descent or even Newton method, he can manage with inexact line search. And with conjugate, it's better to do it accurate because you have this requirement of conjugancy, which at least close to the optimum, our nonlinear function will behave more close to quadratic one, and we expect this minimization to be accurate. But for quadratic case, we just have analytical expression y, because quadratic function, if I look on it in some direction as function of one variable, it remains quadratic. So I have analytical minimum for it. And I will write it gamma k. Gamma k is gk transpose dk. dk transpose q dk with minus. Sorry, it's minus here. And one can do all the manipulation for writing analytically this quadratic function in one direction, but one can understand even in simpler way. If I have function of one variable and it is quadratic, then I can apply Newton method, and one iteration will bring me to the minimum. So what I need for Newton method, I need the first derivative of my function. And what is the derivative in direction d? We'll learn first lectures, directional derivatives. It's exactly a scalar product of gradient with direction. So what is written here is minus f tag f prime in direction d divided like inverse of second derivative, and this is exactly second derivative in direction d. So divided f double prime dt. At our original point. I will write schematically. So I convinced you that this is a Newton method, and this formula is correct. And Now we need to compute gk plus 1. Let's write it again. Gk plus 1 is q xk plus 1 plus b. Okay. And what I say, if you, for example, already computed qdk, for example, for this purpose, for computing step size, you don't need to compute again qx plus 1. And this will save computation, because this is qxk plus gamma k q dk. So we don't need extra multiplication. You should put attention on this when implementing conjugate gradient for quadratic functions. So now only a few words about convergence rate of the conjugate gradient. There are many results, but one of them, if we, first of all, like conjugate direction method, conjugate gradient for quadratic form with n variables, I forgot to say that it should be positive definite quadratic matrix Q. Because otherwise quadratic form, if it's not positive semi-definite, it will decrease to minus infinity. So for quadratic form, we showed in conjugate directions that at most in n iteration, where n is the dimensionality of our problem, the process should converge because of this expanding manifold property. Manifold expands to all the space. But when we solve very large problems with 100,000 variables and so on, usually we don't wait till this point, and much earlier a good solution may be obtained. And one of estimate, if we say that maximal lambda value of our matrix Q is capital M and minimal is small m, lowercase m, then one can say, for example, that norm xk plus 1 is xk, minus x optimal, x star will be optimal point. Less than equal the following expression, square root of capital M minus square root of small m divided by their sum, square root of capital M plus square root of lowercase m. By previous error, xk minus x star. And this expression, when capital M is much larger than small m, is approximately 1 minus 2 square roots of capital by small. And to appreciate how good this result is, we can compare with gradient descent convergence rate. If you remember the formula, the C was approximately 1 minus 2, sorry, here opposite, yes, small divided by capital, because this number should be small. Small divided by capital. So this is a rate for gradient descent, and this is rate for conjugate gradients. For example, if this ratio is million, then sorry. So let's take an example when this ratio, actually it's a condition number of matrix, m by m is like 1 million. Then for conjugate gradients we will get convergence rate like 0.998. And for usual gradients, we will get 0.9999998, and one can understand that it like makes thousands of gradient steps to get the effect of one conjugate gradient step. And this is really important for large-scale computations, and you should also pay attention that the computational cost of one step is about the same. Okay, so like we already told that convergence rate depends on condition number of matrix, despite for conjugate gradients it gets under square root ratio m capital divided by small, but still it's better to us have this ratio as small as possible. And a way to do it is to use preconditioning. So suppose we have to minimize quadratic function, which like 12 symmetric positive definite Q. And let's do change of variables. Suppose we have invertible matrix S, and we denote S like S multiplied by Y. And then we can minimize a related function phi of Y, substituting X into this formula. So we get 1/2 Y transpose S transpose Q SX plus B transpose, SY, B transpose SY. So we get, instead of Q, S transpose QS. And the goal of this manipulation is that sometimes we know somehow this right matrix S which is from one side easy to compute, from other side the condition number of this matrix S transpose QS is better than condition matrix of Q. Then we apply a conjugate gradient in variables y and get our solutions faster, and then we substitute and get optimal mix. For example, sometimes, and it's quite often in practice, matrix Q have large numbers on diagonal, and they are very different. Among those numbers are very large and are relatively small. And what we would like to multiply by some matrix S such that the resulting matrix will have a uniform diagonal. And I will write it explicitly. Example. If Q is near diagonal or diagonally dominated, we use S I will write in the following way. Square root of diag Q, meaning diag Q is diagonal matrix with diagonal elements of Q and other elements are 0, and then I take square roots of these numbers and then take 1 over them. But generally, and this is like taking inverse of this matrix. Or I can even open, if it's a diagonal matrix, on diagonal we have 1 square root of Q 1, 1 over square root of Q 2, so on, and zeros in other places. Yeah, and this is like one example. You can check yourself what will happen with the result if your arbitrary matrix Q will multiply it from both sides by this. There are other kinds of preconditioners. Sometimes you don't. So the best it would be a square root of inverse of Q. If it's like symmetric, then you get identity matrix. But often you can compute approximate inverse of Q. For example, if your problem is related to some discretization of continuous problem and you have more fine and more coarse discretization, you can get approximation for your inverse from considering coarse discretization problem, and this one of ways the people use in differential equations. Another way, if Q is have some good structure of is sparse, for example, one can do Zibulevsky factorization, but Zibulevsky factorization may become difficult numerically from step to step, more and more difficult. So it's called, there is some so-called incomplete Zibulevsky factorization. Do something approximate and use this as a precondition. So, like I told you, just do your conjugate gradient in Y. But actually, at every iteration, you will get some YK, and implicitly you will have XK. And clever people sat and thought a bit and wrote iterations of preconditioning conjugate gradient right in terms of x. And how direct formula. For updating x. For this we will denote W, what was S transpose S. Transpose S. And actually I will write whole method of conjugate gradient. So D0 is W multiplied by G0, and X K plus 1 is XK plus gamma KD K, and DK plus 1 is again W multiplied by G K plus 1 plus beta K dk where beta K is equal G K plus 1 transpose W G K plus 1 divided by G K transpose W G K. So this is already in terms of our original function, and G is this Q x plus B. You can see this is very close to the original conjugate gradient. So we just multiply by W our gradient in computing direction, and when compute beta we multiply by W. And by the way, another advantage of this is that we don't use explicitly matrix S, but instead of we use S transpose S. Why it's good? Because if somebody computes approximation of inverse of Q, he has a symmetric matrix. He doesn't like to find its interpretation as a product of two other matrices. I suggest you just at home to verify that what is written here corresponds to what was told here, that this is methods for minimization in Y when we do such substitution. So, okay. We have learned that with the conjugate gradient we can minimize very large-scale quadratic functions in large number of variables, and minimize quadratic function is the same like solve large system of equations. We will see it right now. And where did we use this large system of equations? For example, in Newton method. And this is gives us our new title, Truncated Newton method. And in the Newton method, at every iteration, we should solve a Newton system. So we stay at some point, we have a gradient at that point, and we have a Hessian at that point of our nonlinear function, which we want to minimize with Newton method. And the Newton direction is computed as a solution of this linear system. Okay, what we can do, we can write the following quadratic form, which is here, d transpose hd plus g transpose d. And I say that the system is an optimality condition for this quadratic form. If I compute gradient of this form with respect to d, so I have hd plus g is equal to 0. Exactly the same. And actually we have one more link. I just want to remind you the derivation of Newton method was minimization of second order Taylor approximation of Newton, which was originally quadratic form. Actually, this is that quadratic form which you get from this formula. And if we have a very large number of variables, say hundreds of thousands, even millions, we often, it would be too costly to solve it explicitly, and even minimized by conjugate gradient exactly would be too costly, like make million of iteration. So instead, we minimize this quadratic form with using conjugate gradient methods with respect to d, only approximately. And because of this, it's named truncated Newton. So we truncate our Newton iteration. One can say formally or informally, we need compute few steps of conjugate gradient for this for this problem. Till some criterion will be met. For example, norm of the gradient of this expression or norm of difference in our equation, h d minus g is plus g, less or equal, for example, some constant divided by this norm before we started our iterations. H d0 plus g. I should stress this d0 with respect to conjugate gradients, not with respect to this external Newton method. So we actually have a nested process. On external iterations, we update d, we do line search and compute new Newton iterates, and in internal we apply conjugate gradient to this auxiliary quadratic problem. So if you remember, the basic computational effort in solving conjugate gradient would be multiply matrix of the quadratic form by something, by some directions, for example. So for very large problem, it will be unrealistic and impractical to compute Hessian explicitly. It will be matrix of million by million. But fortunately, if one asks how much would cost multiply Hessian by arbitrary vector, and the interesting answer is that it will cost about the same as function computation. So you are staying at some point, you have some function f of x, you're staying at some point x, you should compute g shell x, and you want to multiply Hessian at this point x by some arbitrary vector z. So there is a whole theory of differentiation which claims that computing all these three things is about the same up to some very small constant like 3, I don't remember. And you really should put it into account when you do numerical computations. It looks like gradient is a vector having many components, and f is only a scalar. But I will give you an example. For example, I have a quadratic form, x transpose ax. So, how much it would be cost to compute function? I should multiply a by x, this is a major effort, and then by x transpose is cheaper. Because here we have n squared operations, it's here only n. How much it would cost to compute gradient? Actually, after I computed function, it will cost nothing, but one can say that in general, the gradient will be like 2ax, the same as the function. And how much it would be multiply Hessian by some vector is the same. So in this toy example, you see that at least in this case it's right, but you should really put it into consideration that for all problems which you meet in numerical computation, this is right up to some very small constant, and if it's not so in your computation, just check again whether there is a clever way to rationalize what you are doing. Okay, so we need what is written in my records. In process of CG, we have to multiply Hessian by vectors, but we don't need to compute H explicitly. Let me write this. In process of CG, we should multiply H by vectors. Do not need to compute H explicitly. Let me give one more example. For example, let H is equal A transpose B A. Say B is H should be symmetric, so B is symmetric and A is general matrix rectangular. So if even all three matrices n by n multiply two matrices is n cube operations. It's like n operations for every element. So and instead, when I want to multiply H by Z, how I would write it in MATLAB? I would write A transpose B A Z. Some multiplication signs I don't put here. Oh, well, let's write them like in MATLAB. It would be A prime. So, should we do it? Don't do it. Don't do it in this way, because it seems that today MATLAB is not clever enough to understand this. So just put parentheses in the right way. So now I know that my computations are cheap because A by Z is giving a vector. So then I multiply B only by a vector, and then I multiply I prime only by a vector. To finish with this topic, I should mention one more option. Enough from here. I will just write you a formula h multiplied by vector z is approximately g at the point x plus epsilon z minus g is gradient g of x divided by epsilon. So how can I get this formula? You remember definition of Hessian? It works like in this way. Hessian multiplied by differential of x gives differential of gradient. It's pretty similar if I use dx as epsilon z. You immediately see this problem.